Choosing an LLM is no longer a one-time architecture decision. In production, it becomes a routing problem, matching each request to the model that provides enough quality at the right speed, risk level, and cost. So far, you've built the production foundation: architecture, deployment, observability, reliability, security, governance, and cost awareness. Now the focus shifts from making systems work safely to making them operate intelligently by choosing the right model for each request under cost, latency, quality, and risk constraints. In production, model selection is less about finding one best model and more about choosing the right model for the job. A powerful model may deliver strong quality, but add unnecessary cost and latency for simple tasks. A cheaper model may save tokens, but fail when accuracy, safety, or trust matter. The real optimization target is value, the lowest practical cost that still meets the required outcome. A useful model portfolio is more than a list of available models. It is a capability map. Each tier should show what a model is good at, where it is weak, and what trade-offs it creates. Start with core capabilities like reasoning, instruction following, domain accuracy, coding, and tool use. Then add operating constraints: latency, throughput, cost, context length, and availability. Finally, account for market fit and risk, including multilingual quality, tone control, personalization, accessibility, safety behavior, hallucination tendency, compliance, and data handling. Routing becomes systematic when every model is compared on the same dimensions. Before selecting a model, classify the request. Is it a simple transformation such as summarizing, formatting, extracting, or labeling? A smaller model may be enough. Does it require multi-step reasoning, coding, financial judgment, or legal interpretation? Then a stronger model is usually appropriate. Also check the context window, since long documents may require long context models or retrieval. Finally, assess sensitivity and failure impact. Regulated or confidential work may need private, approved, or self-hosted models. Good routing is task assessment turned into a model choice. Dynamic routing adds a decision layer between your application and the available model pool. Instead of hard-coding one model, each request is evaluated at runtime. The router can consider user tier, prompt category, estimated tokens, sensitivity, risk signals, latency targets, and recent model quality metrics. Based on policy, it may choose a hosted model, a private model, an open source endpoint, or a fallback path. The critical requirement is logging every decision, so teams can understand cost, performance, safety outcomes, and why a specific model handled a specific request. Routing does not have to begin with machine learning. Simple rules are often best when the decision is governed by policy, such as customer tier, data sensitivity, region, or compliance. Scoring adds nuance by balancing quality, cost, latency, risk, and availability into one decision. Classifier-based routing goes further by predicting whether the incoming task is simple, moderate, or complex, then choosing the right capability tier. Adaptive routing closes the loop by learning from evaluations, feedback, service-level performance, and cost trends as production evidence accumulates. Think of routing as a decision gate before any model is called. First, identify risk. If a request contains sensitive data, send it only to approved, private, or compliant models. If it is not sensitive, evaluate complexity. Routine summaries, formatting, or classification can use fast, low-cost models when benchmarks show they are good enough. Deeper reasoning, tool use, long context, or domain-specific accuracy should move to stronger models. Finally, define escalation paths. Low confidence, policy triggers, or capability limits should automatically reroute to a safer or more capable option. Reliability-aware routing treats model selection as a live operational decision, not a static preference. The router should check health signals, latency, error rates, quotas, and provider status before sending traffic. If the primary model is down, slow, or unreliable, a circuit breaker can stop repeated failures and move requests to an approved fallback. When full quality cannot be maintained, degrade deliberately. Use a smaller model, reduce context, delay non-critical work, or send cases to human review. Most importantly, track fallback frequency and output quality separately, so resilience does not become silent quality loss. Choosing a model platform is less about ideology and more about where you want complexity to live. Hosted APIs provide fast access to strong frontier models, minimal infrastructure, and simpler scaling. The trade-off is ongoing token cost, vendor dependency, and less control over deployment details. Self-hosting can improve unit economics at high volume and offer tighter control over data residency, latency, and customization. But it also brings GPU capacity planning, serving reliability, monitoring, patching, licensing review, security, and model evaluation. Dedicated private deployments often sit between these two extremes. Model choice should never be based on token price alone. Hosted APIs may look simple, but the bill can include inputs, outputs, embeddings, tool calls, retries, batch processing, and provider fees. Self-hosting may look cheaper at scale, but only if you count GPUs, utilization, auto-scaling waste, engineering time, monitoring, security, and maintenance. The hidden cost is failed task overhead. Low-quality outputs create retries, escalations, manual review, customer frustration, and compliance exposure. A better metric is cost per successful task, what you pay to reliably achieve the business outcome. Good routing starts with evidence, not preference. Build evaluation sets from real production tasks, including easy cases, hard cases, and edge cases that expose failure modes. Then define success from multiple angles. Automated scores, judge models when useful, human review for nuance, and business outcomes when the task affects revenue, risk, or support load. Run each candidate model through the same prompt, retrieval context, guardrails, and post-processing, so the comparison is fair. Track latency percentiles, token use, retries, tool call failures, hallucinations, and safety behavior. The result is a routing policy you can update as models and workloads change. To make cost optimization practical, measure the full cost of successful work. Include tokens, retries, tool calls, fallback models, infrastructure, and human review. Then define what success means for the task. A correct answer, grounded response, completed workflow, approved tone, or safe refusal. Divide total cost by successful tasks and track that number by model tier, user segment, prompt version, and traffic pattern. This reveals the real trade-off. A cheaper model can lose money if it fails often, triggers repeat calls, or sends work to humans. In production, a model router should be operated like any other critical release system. Routing policies need versions, owners, and change history, just like prompts, models, datasets, and indexes. Before a policy reaches users, test it with canaries, A/B comparisons, shadow traffic, and holdout evaluations. After launch, monitor distribution, cost, latency, quality, safety events, fallback rates, and satisfaction. Sensitive routes need approval, and every rollout needs rollback criteria. The goal is simple: improve routing continuously without turning experimentation into uncontrolled production risk. Cost control starts with choosing the right model for each request. Tier models by capability, latency, safety, compliance, and cost. Then route work dynamically at runtime. Compare hosted and self-hosted options through total cost, not token price alone. Next, we optimize execution with caching, batching, rate limits, and performance tuning. Right model, right task, right cost, right time.